Now, over here, interesting questions should come now that I've spoken pretty much in depth about behaviors. A question should obviously occur: why are we doing all this? What happens when we do all such kinds of simulations? There's a bookish definition, which I hate. So, if you want to do weather prediction, you'll have to simulate weather patterns, and you see how beautiful the weather is. So many problems are solved in life by simulation. You want to find out whether for the new movie releasing in a cinema theater near you, which is going to be watched by 200 people at a cinema near you, how much will be the traffic jam? So you simulate that movie and theater and find out what will happen. Sometimes it's more interesting, like the road near the High Court at Prayagraj was being made. Now you need to find out whether you want to cut the schools and tell them that sorry, the schools cannot operate at this time because I've done my simulation, there'll be too much traffic. You want to adjust their timings, you want to disallow people using roads, or you want to make temporary arrangements, you want have to block cars. These are very important decisions for traffic. And how do we make those decisions? You cannot say that, okay, let everything happen. When there's a chaos, then I'll send my traffic havaldar. Sorry, too late. It becomes a mess that you cannot take care of. You have to do simulations before. Fire, how many exits do I have? Which of them are at what places? How many maximum people can come? It's all by simulation. So, of course, simulation helps you answer questions and make decisions. A traffic light near you may be operating from simulation studies. How much time red, how much time green, how much time yellow. The safety plan of one of your football stadiums, cricket stadiums may have been made by simulations, or the aircrafts that you board and deboard may come from simulations. I mean, do you open both gates? You open one gate, in which order do you fill up seats in case of fire? What happens in case of traffic? What happens? So that's one major area of simulation. The other major area of simulation is, of course, interesting movies. How are the animated characters made? They're all simulations. So, virtual armies fighting each other, creatures going around and forming complex patterns, a number of virtual avatars dancing in the background, two armies of virtual characters fighting with each other in a movie plot, or a simulated football game where the players are simulated just for the graphics to show as a background while hero and heroine are interacting, two clothes which are completely digital and having all the nice autumn effect, sometimes simulated. There's a lot of graphic value nowadays, so it's no longer where you'll use in the old and now classic software that create animations. Now you create intelligent animation where each one of the entities, it's reacting to the different weather, light patterns, whoever, whatever is around, and giving you a nice look and feel. So the final animation, unlike classic animators of cartoons, the animators also do not know now. All they do is they create all the entities and they just click on simulate. So in a fabric, every entity, every section, or as we say, every mesh could be simulated. A virtual army, the entire avatar could be simulated. Multiple creatures could be simulated. Multiple entities could be simulated. It will create bad simulation, but you'll add a lot of graphical rendering over the dirty simulation simple entities, and graphics rendering over the AI logic on the simulation is what will drive all of them. The third and one of the most interesting why we do simulations is because of properties called as the emergent properties. So the emergent properties means that system is more than sum of its parts. So I just only taken examples. Favorite machine learning, what's a neuron? Just a weighted addition, activation function. What can it do? If I give you thousands of neurons, you'll be like, what? Why do I need them? It's not solving anything in life. So neurons and the collections are useless, but when you connect them, it becomes all the deep learning and all the wonderful things that biggest people are researching these days. So a neural network is more than the sum of all the individual neurons. Similarly, group projects. I give in the project, I say that, okay, it has 5 parts. Roll number 1, do part number 1. Roll number 2, part 2, do part number 2. Roll number 3, do part number 3. 4, do part number 4. And 5, do part number 5. And you give me my submissions. You'll see, of course, the assignment gets done. All the parts are done. But group projects, what happens? You sit on a discussion table, 5 people. You say, hey, your part is not integrating with mine. You change your design. Why should I change my design? You do it. Did both of you consider that the assumptions that you're making will not hold in the market? Your designs are okay, but it's not solving the problem. You're solving a different problem. So you correct each other, you discuss, and from that discussion, a lot of things comes up. And because a lot of things come up, something is more than the sum of its parts. The knowledge that it creates is more than the sum of its parts. And the integral issues that you solve is more than what you would have never solved by sum of the parts. So we say it's emergent. Panel discussions are emergent. You talk to 5 people individually and make a transcript of all their discussions. It's not as valuable as a panel discussion where people cross-question, they correct each other, they put new issues. So that discussion is the one which says that something is more than sum of its parts, and that's why we are hating the coronavirus period. You are not at the same geographical place. I would have asked each one of you so many questions, and then we would have seen the flow of ideas. So this lecturing is definitely bad, and that collective problem solving, something is more than the sum of its parts. So after neural network, evolutionary computation, what we will be studying. So who would have said that an ant going will lead to the ant colony optimization algorithm? You leave 1,000 ants, they can never find the sugar in your house. They collectively work, leave pheromones, something is more than sum of its parts. The birds chirping outside, none of them would have gone to their correct migration places. They collectively correct each other and go to their migration places. So when the birds fly, they look at each other, they correct each other, and that's how they go. The ants follow the trails of the other ants, that's how they go. That's exactly what the honeybees do. So these are all what are emergent properties, something being more than sum of its parts, and that's what we do in these simulations. We say that we'll be simulating things to get these emergent properties where the simulated system could be a value, even though you see the individual ones and say that it absolutely looks ridiculous. And that's exactly why we say that the artificial life simulation way of thinking is different from the AI way of thinking. So when we say AI, we say that this is the problem that I want to solve. Even in the AI course, I never discussed the philosophical issues of AI. I said that's the problem that I have to solve. These are the algorithmic steps that I'll follow. it's computational rationality, it's algorithmics. So all you say is that I have a problem, I'll divide this problem vertically, horizontally, I'll solve all the parts, I'll look at the nitty-gritties when the things interact, and I'll make a beautiful algorithm overall in a top-down approach. We are discussing the artificial life simulation here. That's a bottom-up approach. You don't say I need to solve this problem. You'll say, look at the ant going, let's simulate it up. Look at the water flowing, let's simulate it up. You look at the birds chirping, let's simulate it up. You look at people moving. That's what I try to do. If you find me roaming in the campus, I'm looking for interesting behaviors so that I can simulate them up. Some of your questions are also from such observations. So, that's what we call as the artificial light simulation. I'm just simulating things up. Eventually, it could lead to interesting observations and interesting behaviors and interesting and powerful algorithms. So, you still have a good algorithm. You've got the ant colony optimization, the particle swarm optimization, you've got the neural network, but you've got it in a bottom-up approach. You just simulated life, you just simulated entities, you just simulated living beings, and that simulation could potentially become an algorithm in a bottom-up approach. So that's what we call as the artificial life simulation, and that's more or less what summarizes what we will be doing around in this particular course, where we will be looking at multiple entities and we'll decide based on behavior how do the entities act in the world, and by deciding how do the entities really go around acting in the world, we will see what beautiful picture does it create, what beautiful simulation does it create as a result of all this up. Now, another interesting term associated with multiple behaviors is called as the dynamic user equilibrium. This time let me just take an example. I say there are two roads, a long road to go to the market and a short road to go to the market. You can choose anyone at this point, so that's the entry point, that's the exit point. Here you decide whether you take this one or this one, and of course you take number 2. Who'll use road number 1, but what happens is that along with time, the density at this road absolutely becomes too high, and this one is probably nobody is taking it up. All shortest route algorithms say it's bad. Now, speed is inversely proportional to density. That means if you take this route, you virtually do not move. It'll take you 1 hour because of the traffic congestion. Now people start taking this route where it's very long, but it makes you reach faster. And because it makes you reach faster, people are using this one. And these people will now, what will they do is, they'll call up their friends and family who are still stuck here, that do not take this route, there's a big traffic jam, take this one. And they calling up will transfer more people around in route number 1. As a result, this density will reduce. And now some of the people here will be able to see that, okay, it looks clear enough, so let me take this route. And that's what we said, that the system has come into a dynamic user equilibrium where taking this route, people do not mind because of the small density and higher speed, even though it's longer and the petrol will be more over here, it will not be economically better. Here, there's a traffic congestion, but it's a short road, and more or less the two of them should eventually end up taking nearly the same time. At any point, if there is, this road becomes more preferable than this, nature will automatically reroute vehicles over here so that this becomes as preferable as this. And hence, subjected to a high density of traffic overall, the two roads become equally likely whenever the density changes in one, the other becomes more valuable, and people start to work to again get that equilibrium. That's what you see in natural life as well. So, what happens if the tigers become too much? They'll eat all the humans, and we'll be taking the schools in heaven. Of course, eventually they'll be short of food and the tigers will die. That means the human life will increase again. Equilibrium. So, each and every species in this ecosystem is under an equilibrium. I took a natural example over now and I took an artificial example over here. Is into an equilibrium, and whenever the equilibrium is broken, the forces of nature change, the forces of this nature over here change to get you into equilibrium again. The only caveat is that the two equilibriums may not be the same equilibrium. So if tigers increase, they eat up most of the humans, and then the tigers die because there are no humans to eat. There's no guarantee that humans will be the best species. Some other kind of animals may dominate the planet, hypothetically speaking. And you look at this equilibrium at each and every point of time. So, a very local example, what happens when we take labs? The lifts are clogged, and then people whom I've seen say, okay, I'm not taking the lift, I'll walk. So walking becomes preferable to them. Otherwise, we know that there are too many students and we have too less lifts. If every student starts using lift, it will be bad. And then these people will also give an excuse, I'm exercising. So the stairs and the lifts in this institute are under a kind of a dynamic user equilibrium. Some people prefer to wait and some people prefer to walk. There are pains and gains in both of them, and dynamic user equilibrium, the pains and gains roughly balance out each other. That's not what happens in low density, that's what happens under high density regions, of course. So, in this course, we'll do in a lot of simulations, and we will take in the best way to simulate is to simulate things that you can see around. So we'll take in lots of virtual universities with virtual maps, and we'll take in lots of Rahul Kalas out over here. We will take in lots of students around over here. We'll also take in a lot of other professors around over here, and we'll make them play games of hide and seek, of avoiding each other, loving each other, having romantic type with each other. Like this could be a couple sitting somewhere, and this could be the security in charge who comes around, and when it comes around over here, these two people get away. So we'll be simulating all these kinds of behaviors as a fun exercise, which in the future, of course, has a potential of all the applications that I have covered.